So, dear students, today we'll cover uh, vibration measuring instrument part. Okay. Uh, as you all know that in most of the vibration systems, the dynamic forces, right? The dynamic forces in a vibratory system depend on the displacement, velocity, and acceleration component of a system. Okay. As you know, the spring force, which we describe mathematically as kx, is proportional to the velocity. Okay, because that x part is to be there. The damping force. Sorry, I'm sorry. This is proportional to displacement. Displacement. The damping force, which we describe as Cx dot, is proportional to the velocity, and the inertia force. Okay. The inertia force, which we call as mx double dot, is proportional to the acceleration. Okay. Therefore, in vibration analysis of a mechanical system, it is required to measure the displacement, velocity, and acceleration components of a system. Okay. The instrument which are used to measure these parameters are known as vibration measuring instruments. Okay. Or We call them as seismic instruments. Okay, a simple model of seismic instrument is as shown in the figure. Okay, now if you draw a simple schematic of a vibration measuring instrument, let's say we have a spring, then we have a damper here connected to the seismic mass. We call this as a seismic mass, right? And everything are kept inside a frame. There will be a frame, and this is the base of the machine, vibration measuring instrument, and the whole setup is resting on a machine on which we need to find out the component, vibration related component, either it may be displacement, velocity, or acceleration. So we can say this is our frame. Uh, we have a scale attached to it here. Yeah. So this is our scale, and the spring is having a stiffness K, the damping coefficient is C, the mass is having a displacement, let's say X, the base is having a displacement of Y sine omega t, Y as capital, okay, and this is our machine. This is the machine. Okay. Now the measure requirement, can write the measure, sorry, the measure requirement of a seismic instrument is to indicate an output which represents an input such as the displacement amplitude, velocity, it may be velocity or acceleration of a vibrating system as close as possible. Means it should reflect the result as close as possible. Okay. Now let M is the seismic mass, C is the damping coefficient, is the damping coefficient of the seismic unit. Okay. K is the stiffness of spring used. X is the absolute displacement. So where X is the absolute displacement of the seismic mass, okay. Y is the base excitation. Okay. Now let's say we have a relative velocity component. We'll describe this as J. It will be denoted by X minus Y. Okay. Now this is the displacement of seismic mass relative to the frame, we can say, right? Now the equation of motion of seismic mass can be represented as mx double dot plus c x dot minus y dot plus k x minus y is equal to 0. Let this be equation 1, and we can write this equation 1 as m z double dot plus c z dot plus k z is equal to uh, minus my double dot, right? Let's say this is equation 2, because we introduce z here. Z is x minus y. Okay, so that y term will come to here. Okay, when you add on this left side, it becomes x again. Okay. So assuming base excitation to be SHM, simple harmonic motion, we'll assume a solution y as capital Y sine omega t. Let's say this is equation 3. So we can write the velocity component dy by dt as omega y cos omega t, and y dot double dot, the acceleration will be minus omega square y sine omega t. Let's say this is equation 4. Okay. Now substituting the value of y double dot in equation 2, we'll have mz double dot plus cz dot plus kz is equal to m omega square capital Y sine omega t. Let this be equation 5. Now this above equation 5, right, the equation 5 represents the equation of motion of a forced vibration, with uh, this component m omega square capital Y as f. Instead of f, we are writing here m omega square Y. And solution to the governing differential equation is z is equal to z complementary plus z particular solution, where zc is a complementary solution which nullifies, which get nullified after some time, after some time. So the total solution, is only a steady state solution ZT. Okay. Now let the steady state solution uh, of equation 5 is mm, small z is equal to capital Z sine omega t minus 5. Let's say this is equation 6. Now this equation 6 has to satisfy equation 5. The amplitude of steady state vibration is denoted by Z equal to m omega square capital Y k minus m omega square whole square plus c omega square whole root over. Instead of f, we substitute this m omega square y. This equation we have already got in the displacement form of forced vibration equation. Okay. Now dividing both numerator and denominator by k, this z value will be equal to omega by omega n y 1 minus omega by omega n square whole square plus 2 zeta omega by omega n square. Okay, whole root over. This will be equation 7. Now substituting equation 7 in equation 6 we have z equal to omega by omega n square y 1 minus omega by omega n square whole square plus 2 zeta omega by omega n whole square whole root over will multiply by sine omega t minus phi. Okay. Instead of capital Z, we substituted this value. Okay, let this be equation 8. Okay. Now the phase angle is phi, which is equal to tan inverse of c omega divided by k minus m omega square. Okay. If you further simplify this, you'll get phi as tan inverse 2 zeta omega by omega n, okay, divided by 1 minus omega by omega n square. This will be the value of the phase angle. Let this be equation 9. Okay. So from equation 8, you can say from equation 8, we have the ratio of z by y. It will be equal to omega by omega n square divided by 1 minus omega by omega n square whole square plus 2 zeta omega by omega n square whole root over sine omega t minus phi. Let this be equation 10. Now this is the ratio of the relative velocity divided by the base excitation displacement. Okay. Now the variation the variation of z by y with respect to frequency ratio omega by omega n can be plotted, and we in the subsequent class will cover this part, and we'll go on for your displacement measuring instrument, then by velocity pickups, okay, transducers, tachometers, etc. Okay. So for the time being, we'll cover this much only. Thank you.